Hello friends, last time we have learnt about three terms: accuracy, precision and error, and today we take up significant figures. The least count of meter scale is 1 millimeter. The least count of meter scale is 1 millimeter, and an observation may be beyond 10.2 and a little less than 10.3 centimeter as shown in diagram. Different students record lengths as 10.27, 10.28 and 10.29 centimeter respectively. Now here reliable digits are 3. 10.2 is reliable. Now uncertain or doubtful digit is 1, that is 0.07, 0.08 or 0.09. Thus, the digits that are exactly known and the last uncertain or doubtful digit in a measurement are known as significant figures. I repeat, the digits that are exactly known and the last uncertain or doubtful digit in a measurement are known as significant figures. That is, number of significant figures in a measurement are given as number of reliable digits plus last uncertain or doubtful digit. I repeat, the number of significant figures in a measurement are given as number of reliable digits plus last uncertain or doubtful digit. Now we illustrate it with examples. For example, the time period of oscillation of a simple pendulum is 2.6 seconds. Number of significant figures is equal to reliable 1 plus doubtful 1, that is equal to 2. A reliable 1 means 2, doubtful 1 means 6. So number of significant figures is reliable 1 plus doubtful 1 equal to 2. Example 2, length of an object is 237.5 centimeter. So number of significant figures are equal to reliable 3, that is 237, plus doubtful 1, that is 5. So total number of significant figures is equal to 3 plus 1 equal to 4. 3 plus 1 equal to 4. And now rules of significant figures. First rule, number of significant figures does not vary by changing different units. I repeat, number of significant figures does not vary by changing different units. For example, length of an object is 237.5 centimeter in CGS system. Number of significant figures is equal to 4, that is 3 plus 1, 3 reliable plus 1 uncertain. Also, the length of an object can also be expressed as 2.375 meter in MKS system. Again, number of significant figures are 4, that is reliable 3, uncertain 1. Now we see that the number of significant figures does not vary by changing units from CGS system to MKS system. Now another point we have to mark is that decimal does not separate reliable and uncertain digits, because the last digit is normally uncertain. Now this takes us to the second rule, That is, position of decimal does not affect number of significant figures. I repeat, position of decimal does not affect number of significant figures. For example, because it is customary to write the decimal after first digit. Therefore, the length of an object 237.5 centimeter is required to be expressed as 2.375 into 10 raised to power 2 centimeters, and number of significant figures are 4. So thus we see that position of decimal does not affect number of significant figures. Okay. Example 2. Mass of an object is measured to be 0.0345 kgs. Number of significant figures are 3. It can also be written as 3.45 into 10 raised to power minus 2 kg. Again, number of significant figures are 3. Thus we see that decimal does not affect number of significant figures. Now example 3. A measurement is written as 2.5400 centimeter. Number of significant figures are 5. The inclusion of last zeros indicate that measurement is made to 5 significant figures. What we have to mark here is inclusion of last zeros indicate that measurement is made up to 5 significant figures. So, rule 3. All the non-zero digits are significant. For example, length of an object is made to be 2.375 centimeters. So number of significant figures are 4. Rule 4. All the zeros between two non-zero digits are significant. For example, a certain measurement is 0.002308 centimeter, and it can be expressed as 2.308 into 10 raised to power minus 3 centimeter. Therefore, number of significant figures are 4. The zeros after decimal are not significant. Example 2. In a measurement 108.006 centimeter, which can be expressed as 1.08006 into 10 raised to power 2 centimeters. Number of significant figures are 6. It means all zeros which are in between non-zero digits are significant. Rule number 5. The trailing or terminal zeros in a measurement are not significant. For example, one astronomical unit can be expressed as shown, which is equal to 1.49 into 10 raised to power 11 meter. Now here number of significant figures are 3. The trailing zeros are not significant, or terminal zeros are not significant. Now rule 6. The trailing zeros in a number with decimal point are significant. I repeat, the trailing zeros in a number with decimal points are significant. For example, consider a measurement 0.25400. Here number of significant figures are 5. We have taken into account the trailing zeros after 254. It shows that the trailing zeros in a number with decimal points are significant. Now rule number 7. If the number is less than 1, the zeros on the right of the decimal point and left of non-zero digits are non-significant. I repeat, if the number is less than 1, the zeros on the right of the decimal point and left of non-zero digit are not significant. For example, consider the measurement 0.025400. Here number of significant figures are 5. So this 0 after decimal and before 2 is not significant, whereas the trailing zeros are significant. Now assignment number 2.3 continued. Question number 5. Identify number of significant figures in the following. Number 1, 15678. Number 2, 108.006. Number 3, 0.00967. Number 4, 30.00. Number 5, 0.07800. Number 6, 20.20. Number 7, 2020 into 10 raised to power 3. Number 8, 1.496 into 10 raised to power 11. And you write down the number of significant figures on your notebook. Here answers are given to you, and you can verify this after writing on your notebook. You can verify the answer. Now rule number 8, regarding mathematical operations like addition, subtraction, multiplication and division. How is the rule? The final result should retain as many significant figures as are there in the original number with least precise measurement. I repeat, the final result should retain as many significant figures as are there in the original number with least precise measurement. For example, case of addition, if we add 436.32 gram plus 227.2 gram plus 0.301 gram, which is equal to 663.821 grams, and we write it up to 4 significant figures, 663.8 gram, because least precise measurement in the original value is 227.2 gram, which has 4 significant figures. So final result we write up to 4 significant figures. Now example 2, case of subtraction. If we subtract 0.307 minus 0.304, which is equal to 0.003, and 0.307 minus 0.207, which is equal to 0.100. So we write the final result up to 3 significant figures, because original numbers have least precise measurement up to 3 significant figures. Now example 3, case of multiplication. 1 light year, which is equal to c into t, which is equal to 3.00 into 10 to 8 meter per second into 3.156 into 10 raised to power 7 seconds, and it is equal to 9.46 into 10 raised to power 15 meter. So in the original number, least precise measurement has 3 significant figures, so we write the final result up to 3 significant figures. Example 4, case of division. Mass of an object is equal to 4.237 gram and its volume is 2.51 centimeter cube. Its density rho is 4.237 divided by 2.51, which is equal to this. So it is equivalent to the calculated value of density to such a precision when the measurement on which the value is based have much less precision. Therefore, final result should be 1.69 grams per centimeter cube, which is consistent with the precision of the input value of 2.51 centimeter cube. Okay, so here you have 3 significant figures, so final result must have 3 significant figures. Now number 9, rules for rounding off. The result of computation with approximation follow the under mentioned rules. I repeat, the result of computation with approximation follow the under mentioned rules. Number 1, the preceding digit is raised by 1 if last uncertain digit is more than 5 and left unchanged if less than 5. For example, 2.746 can be expressed as 2.75. Initially, significant figures are 4. After rounding off, reduces to 3. And also, 2.743 can be expressed as equal to 2.74. Initially, significant figures are 4 and after rounding off, reduced to 3. Now, second rule for rounding off. If the preceding digit is even, then 5 is dropped. If odd, then preceding digit is raised by 1. For example, 2.75 can be expressed as 2.8 and 2.85 can be expressed as 2.8. Now number 3. In multi-step calculations, one digit more than significant figures is retained and rounded off to proper significant figures at the end of calculation. Otherwise, rounding errors will build up. Let us illustrate with example. For example, consider reciprocal of 9.58 and is calculated as 1 by 9.8 equal to 0.104. Now calculated after rounding off to same number of significant figures, which is equal to 0.104. Now initially in 9.58 the significant figures are 3 and the calculated value also contain 3 significant figures. And when we calculate reciprocal of 0.104, that is 1 by 0.104, it comes out to be 9.62. So there is error introduced. If we calculate one digit more in the initial calculation, then error will not build up. Let us see how it is. If we take one significant more than reciprocal of 9.58, which is equal to 0.1044, and reciprocal of 0.1044, that is 1 divided by 0.1004, is equal to 9.58, the original value. So here rounding error has not crept into, so no rounding error creeps into in this way. So we must take one digit more in multi-step calculations. One digit more than significant figure must be retained and rounded off to proper significant figures at the end of calculation. Then the rounding error will not creep into. Assignment 2.3 continued. Question number 6. Calculate the value of the following. Velocity of light c is equal to 1 divided by under root of mu 0 epsilon 0, where mu 0 is equal to 4 pi into 10 raised to the power minus 7 Henry per meter, and epsilon 0 is equal to 8.85 into 10 raised to the power minus 12 Coulomb square per Newton per meter square. Calculate the ratio of circumference to diameter of a circle. So thank you so much. Tomorrow we'll continue with this topic again, the next part of it. Thank you so much. God bless you.